Okay, so today's video is going to cover the atomic models. We're going to look at the Bohr's model and electron arrangement, and we're going to look at the Lewis structure and how the valence electrons are organized around the nucleus and how we can also use that for making chemical bonds. So let's begin. In 1913, the Bohr's model was created, of course, by Niels Bohr, and he theorized that the electrons are in fixed orbits around the nucleus. These fixed orbits are also known as energy levels or electron shells. Typically, when you want to know how many energy levels exist around a nucleus, you look at the periods. Remember, the periods are the horizontal rows. So when we look at period 1, or row 1, it tells us that there's only one energy level or ring around the nucleus. If we go to period 3, then the same thing applies. Instead of one energy level or one ring around the nucleus, we have 3 rings around the nucleus, and then so forth and so on for every other period. Now, on each period, there's a certain amount of electrons that can fit. The closer to the nucleus indicates that the energy level has the least amount of energy. So the further away the energy levels appear, then the more energy they contain on those energy levels. So on the first energy level, only 2 electrons can fit. On the second energy level, you have 8 electrons. And then on the third energy level, you have 18 electrons. And we only need to go over the first 4 for this part of the presentation, and so that we can solve a few of the items that we want to work on in class. So let's do a few examples. Okay, so our first example, we'll start with lithium. Okay, so lithium All right, so instead of drawing out the nucleus, one thing that we can do is just write the chemical symbol. All right, so this is the chemical symbol for lithium. And lithium is in period 2. That means it has 2 energy levels. So we're going to go ahead and draw first energy level, and we're going to draw our second energy level. We're going to look at the number of electrons. So lithium has, its atomic number is 3, and so we know that it has 3 protons. We also know that when it's in a neutral state, that the number of protons is also the same as the number of electrons. So in this case, we have 3 electrons. Now, if we go back to our chart, we said that on the first energy level, we have 2 electrons. On our second energy level, you can have up to 8 electrons. And then on the third energy level, you can have up to 18. Since we have 3 electrons in lithium, we're going to go ahead and put the first 2 on the first energy level, the one with the least amount of energy. And then we're going to put our final electron on the next energy level. So this is the Bohr's model for lithium. All right, now let's try another one. Let's look at sulfur. And sulfur is in period, this is period 1, this is period 2, this is period 3, and here's sulfur. So we have 3 rings, 1, 2, 3. All right, and again, on our first ring, we have 2 electrons, second ring, 8 electrons, and the third ring up to 18 electrons. In this particular case, sulfur has 16 electrons. So we're going to take and put the first on that first energy level. So that now brings us down to 14 that we have remaining. Remember, we can only put up to 8, so we'll put the next 8 on this level. 1, 2, 3, 4, 5, 6, 7, 8. And now that leaves us with 6 more electrons. So we're going to put the remaining 6 on the third energy level. 1, 2, 3, 4, 5, 6. And this would be the Bohr's model for sulfur. Okay, so for extra independent practice, why don't you try creating the Bohr's model for potassium and for neon, and let's go with magnesium. So try creating the Bohr's model for those 3 elements. Now let's look at the Lewis structure. The Lewis structure was created by Lewis, Kossel, and Langmuir, and it's also known as the electron dot diagram. And in this case, all we're focused on would be the valence electrons. And these, again, are the electrons that are the furthest away from the nucleus. They're on the energy level that has the most amount of energy because, again, it is the furthest away. And we use the Lewis structure when we're trying to make sense of chemical bonds. Now, in order to remember or figure out how to identify the number of valence electrons, you simply look at the group. The group tells you, the group or column tells you the number of valence electrons. And for practicing, we're going to ignore columns 3 through 12, which consist of primarily your transition metals. So we're going to ignore this section here. And we're just going to look at columns 1, 2, and 13 through 18. So if you have an element in group 1, it equals 1 valence electron. That means there's only 1 valence electron the furthest away from the nucleus. So everything in group 1 has 1 valence electron. Remember that valence electrons, elements that have the same number of valence electrons share the same or similar chemical properties. Group 2 means you have 2 valence electrons. Group 13 is where you have 3 valence electrons. Group 14, 4, all the way to group 17, you have 7. And then in group 18, you have 8 valence electrons. But we have to be careful about helium because helium only has 1 energy level when we look at the period. And so it is already satisfied once it has 2 valence electrons on that first energy level. So it's already complete. Okay, so let's go ahead, dive right on in. And we have our periodic table in front of us. And we're going to go back and look at lithium again. Now, when we drew the picture earlier, we had lithium, the Bohr's model, we had, because it's in the second period, we had 2 energy levels. And it has 3 electrons, so we put the 3 electrons in their designated slots. And if you look here, we have this electron, which is the furthest away from the nucleus. And so this is our valence electron. And if we look in column 1, we can also match that up because, again, group 1 indicates that every element in this group has the same number of valence electrons. So simply, when we're trying to make the Lewis structure, all we do is write the chemical symbol, and then we placed the valence electron, in this case, on top of the symbol. Now, just a word of caution, if you decide to do the electron dot diagram or Lewis structure and place your electrons going to the right or clockwise, you must maintain that it must be consistent. If you decide to go from the top to the left, wherever you start, if you go clockwise, you need to keep it consistent. If you go counterclockwise with placing your dots, then it must be consistent. So that's what lithium would look like. Now let's look at beryllium. Beryllium is in group 2, so it has 2 valence electrons. So I'm going to go ahead and put my first valence electron here. I'm going to put my next valence electron here. Then I'm going to go over to boron. And boron is in group 13, and elements in group 13 have 3 valence electrons. So I'm going to put the first one here, the second one here, the third one here, and now I'm going to look for carbon, and carbon is in group 14, and so it has 4 valence electrons. So 1, 2, 3, that wasn't a really nice one there, there we go, and 4. So we have 4 valence electrons. By the time we get to neon, neon is in group 18, it has 8 valence electrons. So in this case, we would do 1, 2, 3, 4, 5, 6. Notice how I'm moving around the element. 7, 8. And now I have completed the electron dot diagram for neon, carbon, beryllium, lithium, and boron. So why don't you give it a shot, and why don't you work out magnesium, aluminum, oxygen, chlorine. So try those 4 and see if you can put together the Lewis structure for those elements. If you look in the description box below, you will see additional resources that cover both the Bohrs model and Lewis structure. That's it for now.